Hey guys, it's Mr. Wolfe here, and we're going to be going over hang time, which is going to be the second part of Target 5. So before we looked at an object in free fall after it's been released from rest, now we're going to be looking at what happens when we launch an object upwards. Okay? So to start this video, let's look at a specific example of an object being launched upwards. In this case, a basketball. So I was actually at this game. The game's tied 104-104 with about 10 seconds left, and Derrick Rose has the ball. All right, so at this point, the ball's been launched upwards, and the ball is right here. And what I want you guys to do is on your target sheet, I want you guys to draw a free body diagram prediction of what you think the forces are that are acting on the ball. And so the ball has left Derrick Rose's hands. It is traveling upwards, so it does have a velocity. What are the forces acting on the basketball? All right. So before I go over what's actually happening once the ball's at this point in the air, let's look at what's going on when the ball is in contact with Derrick Rose's hands. All right, so when Derrick Rose is in the process of shooting the ball, he is applying a force to the ball. So we could say this is the applied force to the ball. And gravity is definitely present, so it's forcing the ball downwards. And notice that our applied force has a greater magnitude than our force of gravity, and that's why our ball is able to accelerate upwards. Now, once the ball leaves Derrick Rose's hands, it had a velocity as it was accelerating in his hands. Once it leaves his hands, we're going to stick with Newton's first law. It's going to want to continue in motion. So the ball still is traveling upwards, but since it's not in contact with his hands anymore, we can include that applied force. And so the only force that's existing as this ball is traveling upwards is the force of gravity. All right, so let's go back to that shot.
Watch this. Step back. Let me step back and kiss myself. In the air, color flash. I tell you what.
All right, so let's go back to the physics. So let's draw a motion diagram for an object that's being launched upwards. As it's being launched upwards, it has that initial velocity, all right? But since the only force that's acting on it is gravity, and that's going to cause it to accelerate by decreasing its speed. Once the ball or any object is at its highest point, the object's instantaneous velocity is at rest. It's going at 0 meters per second. All right, so for a split second, it's at 0 meters per second, and we always have that constant force, that constant acceleration of 9.8 meters per second squared, and now our ball or our object is going to start to increase speed downwards. So if we look at this, at its highest point, it's at rest, and it's accelerating downwards with only the force of gravity acting on it. This part right here of our object traveling downwards is exactly like free fall. And this is going to help us solve many of our hang time problems. So let's now look at hang time through graphing. And what I'm going to do with these graphs right here is I'm going to draw a line directly through them, this dotted line. And what this dotted line represents is the time that our object has a velocity equal to 0 meters per second when it's at that very peak. All right. So on its way traveling upwards, our ball has a velocity. And so we're going to want to draw a slope to this graph, right? Because the slope of a distance versus time graph is velocity. And as that ball travels upward, it slows down. So we need to make our slope, our velocity, start to get less and less steep. So now our slope is 0, our velocity is 0 right when it's at its peak. Now it's going to start to increase speed downwards. And so we just need to make that slope steeper and steeper and steeper going downwards. And so even though our line is going downwards, our slope is less steep here compared to here. So our velocity is increasing. Let's look at the velocity versus time graph. When the ball is initially launched up in the air, it has a velocity. And so we're going to put our initial point right about here. Right? And as it goes upwards, the ball is going to decrease its speed, so its velocity is going to increase its speed until it gets to that highest point where the velocity is 0. Now the ball is going to start to increase its speed towards the ground, so we could go about this multiple ways with our graph. One way is to just draw our line going straight down like this. And what this is representing is that our velocity is getting greater, just the direction our object is traveling in has changed. Now, we rarely work with vectors in CP physics, so you guys could also just draw this as the velocity increasing this way. The reason why I like to draw the graph like this is the slope of our graph is acceleration. And if we draw the graph including vectors, our acceleration this entire time does not change. Even when the ball is at 0 meters per second, it's not like gravity just stopped. It's still acting on the ball the entire time that it's in the air. Those are our velocity versus time and our distance versus time graphs. One thing I do want to go over for our distance versus time graph, and this is a misconception that students have sometimes, is that this line does not represent the path of the object. We could still have this graph if we threw, let's say, a baseball straight up in the air and straight back down. Because remember, our line here is not the trajectory of the ball, it represents our slope, our velocity of the ball. So let's apply the ideas of hang time, the principles of hang time, to some problems. So Derrick Rose has a vertical leap of 1.01 meters. We want to find his hang time. And we say we want to find his hang time, we're looking for the time it takes him to go up and down. So how do we go about doing this? Well, we know how to calculate the time it takes Derrick Rose to go down, right? Because at this point right here, his velocity is going to be 0 meters per second. And this is just going to be like a free fall equation. So let's first solve for the time it takes Derrick Rose to fall down. We know that the distance he's going to travel is going to be negative 1.01 meters. The reason I'm putting negative is because he's traveling downwards. And we know that our acceleration due to gravity is always going to be that negative 9.8 meters per second squared. We know his initial velocity at that highest point is going to be 0 meters per second. And we're going to be looking for the time it takes to go down. So let's solve this just like a free fall equation, where we have our change in distance is equal to 1/2 acceleration multiplied by time squared. Change in distance is negative 1.01 meters. 1/2 negative 9.8 meters per second squared times squared. To get through some of the math on this, we're going to see that t squared is equal to 0.206. So we need to just square both sides, and we're going to get the time that it takes, remember this is just for the time it takes to go down, to equal 0.45 seconds. So keep in mind, we have not yet calculated Derrick Rose's hang time. We've only calculated the time it takes to go down. So how do we figure out the time it takes to go up? Well, it turns out that the time that it takes to go down is equal to the time it takes an object to go up. So if it took Derrick Rose 0.45 seconds to fall down, it's going to take him 0.45 seconds to go up. So all we have to do is just multiply this number by 2. So 0.45 seconds times 2, we're going to get our time to go up and down to be 0.90 seconds. Right? And this is our hang time. All right, so let's look at the last problem. Find Derrick Rose's initial jump speed. Well, when we were working with free fall problems, we were able to figure out the speed that an object has just before it hits the ground, right? And we use this equation right here, V equals v initial plus at. That's only for the velocity when Derrick Rose hits the ground. So what we could do though is let's look at our graphs. Here is our velocity when Derrick Rose hits the ground, just before he hits the ground right here. If we go over, that's the exact same speed that Derrick Rose had when he initially launched off the ground. And we could apply the same idea to our distance versus time graph. So for instance, let's say at this distance, we have a velocity with a slope right here, and we go over, and we have a slope like this. So even though our slopes are going in different directions, they essentially have the same value. Any point for an object traveling up, it has the exact same velocity going up or down. The only difference is the direction of that velocity. So we could say that the initial jump velocity has the same magnitude, but different direction as the landing velocity. So we know how to calculate our landing velocity from free fall. So by figuring this out, we can determine the initial jump velocity. And so we have our variables as we know that our initial velocity, and we're going to treat this like a free fall problem, is 0 meters per second for trying to figure out the landing velocity. Our acceleration due to gravity is that negative 9.8 meters per second. And time is the trickiest part here. So we can't use the hang time for solving the landing velocity because we only care about looking for the point at which Derrick Rose was at 0 meters per second and then fell to the ground and then his velocity right here. So we're going to be we're going to plug in the time it took for Derrick Rose to go down. So time down is 0.45 seconds. So from this, I want you guys to answer and find a value for this question right here. And that does it for our video on hang time.